quickly go through it before we get started. So the project teams are here. So if you click on it, you can click on this, you can see your teams. So please take a look at it and try to contact your teammates. And of course, if you have any concerns, questions, let me know as soon as possible. Okay, so I think that's, any questions about that before I move on? Okay, no, everyone's good? Okay, I can hear you, so you can shout. So the first assignment is also posted here, so you can see. So most importantly, make sure you contact your team members via Canvas. In fact, what I recommend is create a collaboration on Canvas with your team members. And I think, let me show you actually. It's this is here. So Peter, for instance, has created a collaboration, I believe, with his team members. So everyone can do that yourself. You can just start a new collaboration. This is Canvas. And of course, if you have any questions, just send me a note or ask Subhashish, the TA, to help you. Okay, so first assignment is also posted here. So all the assignments will be posted here as well as in Canvas. The first assignment is due September 15th, okay? So you have 2 weeks roughly. And it consists of basically 3 steps. Number 1, pick a name for your team. So it's pretty simple. So I can refer to you in some fashion as opposed to team 1, team 2. So step 2, pick a time for the team to meet regularly, and this can be once a week, twice a week, whatever you want, or it can be once every 2 weeks, whatever. I don't care. It's up to you. And remotely is fine, so you can meet on Canvas or whatever. So in Canvas also you can chat, so it's relatively straightforward. Number 3 is, of course, most important. You need to submit a very brief report. It doesn't, I said less than 1 page here, but it doesn't need to be. In fact, I was going to modify it. It can be 1 or 2 pages if you want, as a PDF, and you can send it to me by email or submit by Canvas or whatever. And I'll give you more detail about this during the lecture today. For the online team, also must do the same report. Just keep that in mind. Okay, any questions before we jump in about the assignment? Okay, I guess not. So let's get started. You can see this, right, Subhashish?
Yeah, I have a quick question.
Sure, go ahead.
So we have a project that we're assigned to look like on there, direct on the team.
Sorry, could you repeat your question? I didn't quite hear it. Or maybe Subhashish, can you repeat it for me?
So in the team list, we're all grouped under a topic.
Yes. Yes.
That topic we're required to tackle, or is it open, or is that just opening and starting point?
So yeah, I assigned the topics based on some feedback that some of you gave me. Some of the students I just assigned because they didn't give me any feedback. If you prefer something different or you want to explore something else, just let me know. But at this point, what I'm expecting is you stick to the topic I assigned. But of course, I'm flexible. So if you think, okay, you want to really do something else, just let me know. But you also have to convince your teammates. That's the only constraint at this point.
Okay, thank you.
Okay, great. Anything else? Anyone else? Okay, I think it's pretty clear, right? And things will get clearer as we go along, because I will give you very specific instructions for each of the assignments and presentations. You will see that. So yeah, don't worry too much, about it. Okay, so today our goal is to really understand some of the basic fundamentals of sunlight. This is very important because we need to kind of set the basic framework for everything that comes later on in the semester. Okay, and we'll look at the schedule towards the end as well. So, of course, we know sunlight's the source of all of Earth's energy. Of course, gives us heat, provides energy for photosynthesis, for food. And even fossil fuels that are used, oil, gas, everything are essentially stored solar energy from millions of years ago, because biomass essentially gets converted into fossil fuels. Biomass is, we will see later on, is the most common fuel that's used around the world, and essentially it refers to plants and dead trees and things like that. It, in a sense, it converts solar energy to fuel used for heating, cooking, whatever. Even wind energy is the result of solar, because it's because of air gets heated up in certain regions, and also it's related to its rotation, of course. Hydropower is also generated by the sun, in the sense that evaporated water returns to earth as rain and fills the dams and can be used for hydropower. So solar is, in a sense, fundamental to all forms of energy that we're interested in. So what is sunlight? Sunlight is, of course, a form of light. So we need to understand the basic properties of light. And the most fundamental understanding of light comes from what we refer to as the electromagnetic spectrum. So this should be familiar to most of you. So let's just review it very briefly. So the electromagnetic spectrum can be thought of in terms of wavelength, which is written in meters here, which can go from, let's say, 1,000 meters, which is radio waves, all the way down to a billionth of a meter, which are the gamma rays. So it spans radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma rays. So this refers to the wavelength of light, which, if you look at the plot here, this shows the wavelength in terms of in a scale. So for instance, when the two peaks of the wave are far apart, that means the wavelength is very large. When the two peaks of the wave are very close together, the wavelength is very short. So this is kind of a very important way to think about the distribution of wavelengths in an electromagnetic spectrum. Now, of course, the reason we're talking about this is because sunlight has a very broad spectrum, and broad in the sense that you get mostly visible light and also quite a bit of infrared light. So we are kind of around here for sunlight. A more familiar way to think about this is in frequency. So in frequency, we'll relate wavelength and frequency shortly, but in frequency is written here. It's in hertz, or cycles per second. It goes as in the opposite sense. So in other words, as the wavelength decreases from left to right, the frequency increases from left to right. So it goes from 10 raised to 4 cycles per second for radio waves to 10 raised to 20 cycles per second for gamma rays. Whoops, let me just quit my thing so it doesn't bother us. Okay, there we go. But what we are, of course, most concerned about is the visible part of the spectrum, which is just a small slice of the entire electromagnetic spectrum. If you zoom out, we get something like this. We magnify this region. So this is the visible part of the spectrum. The red light has lower frequency than the violet or the blue light. And the red light has longer wavelength than the violet or blue light. Okay, and we'll come back to this again and again. So this is kind of the big picture. Now, how do we relate wavelength and frequency? This is something you learned in high school physics. So the basic properties of light is defined by this equation, where the energy of a photon is the Planck's constant multiplied by the frequency of the photon, or nu. Okay, the frequency of the photon itself is related to the wavelength by c over lambda, where c is the speed of light, which is, of course, fixed in a given medium. In vacuum, it's about 3 times 10 to the power of 8 meters per second. Now, from our understanding of physics, and particularly from quantum mechanics, we know that light exists as a wave and a particle, right? It is dual wave-particle duality. So as a wave, it has properties of wavelength and frequency, which is what we just saw in the last slide. But as a particle, it is, you think about it as acting like a billiard ball or some ball, which is a photon, which now carries momentum and, of course, has energy. And these things are related through this equation, the waves and particles. So h nu, representing the frequency and the energy of the particle, is related to the wave as hc over lambda. Okay. Now, these things are very important, although these things are abstract. from our point of view, they're fairly fundamental. But these are this intuitive understanding of this is very important when we start thinking about how we harness the energy of these photons. Okay, so the most important characteristics of light that are relevant to this class are the following. One is the spectral content of incident light. What that means is, what is the color of the light? What is the wavelength of the light that comes in, that we are trying to capture, that we're trying to utilize, whether it's for photovoltaics for solar cells, or whether it's for solar thermal applications or whatnot. The second feature that's important is the radiant power density. What this means is how much energy per unit area, per unit time is coming into our system. Okay, we'll look at this in more detail as we go along. The third thing is, of course, the angle at which the incident sunlight strikes an absorber. So let's say we're trying to absorb the light using a photovoltaic panel. The angle is very important, as we talked about during the first lecture. The last thing is the radiant energy from sun throughout the year. So in other words, how does the energy change with seasons, with time during the day, and so on? Because this is also very important, as we know, when we start building systems that need to be reliable. Okay, so in summary, although we have a lot of properties of light that are very important for engineering and physics in general, the most important parameters that are for our class is listed here, and this is what we'll focus on. Okay, so let's dig in a little bit more into the basic properties of light. First, the energy of the photon. Of course, this is a class about energy, and we are trying to collect photons, so we need to understand what the energy of a single photon is. Okay, as I said before, E is given by h nu or hc over lambda, and h, the Planck's constant, is this number right here. It's a very, very small number, 6.626 times 10 to the power minus 34 joule seconds. Now, the units are important. Remember, energy is in units of joules. Planck's constant is in units of joule seconds. So Planck's constant times frequency, which is in units of 1/2 gives me joules. So that's consistent. And you can figure out the same thing over here, as we'll do later on. Okay? Now, because these numbers are really small, because you can see that's a really tiny number, we can also express energy in electron volts. Electron volts is a very convenient unit when we are talking about single particles. So 1 electron volt is the energy required to raise an electron through a 1 volt potential. All it means is that if you have an electron at the ground of a terminal and you accelerate it by a voltage of 1 volt, that the kinetic energy acquired by that electron is 1 electron volts. It's just a unit of energy. And it can be shown it's equal to 1.6 times 10 raised to minus 19 joules. So it's a very small number, but it's a nice small number that can be used to compute the energy of single particles. Okay? So at this point, I want you to do this calculation. I want you to do it because the goal here is not to do the algebra, but the goal here is for you to get some insight into what is the scale of the energy we're talking about. Okay, so take out your piece of paper and try to do this calculation. It's pretty simple, and you can discuss with your neighbor. So what is the energy of a green photon? A green photon has a wavelength of 500 nanometers, and if you go back to this plot here, you will see the green is right here, which is roughly about 1 micron. It's actually slightly less. It's about here. So it's about half a micron, which is 500 nanometers. So we'll come back to your question. So let's try to answer this question. And you can discuss among yourselves. I'll give you about 30 seconds. After that, Subhashish will work it out on the board. Okay. Just an order of magnitude is fine. And feel free to talk if you want. Okay, so Subhashish, can you quickly work it out? It's of course, to do this is very simple. You apply this equation. It's h, which is this number, which is roughly 10 raised to minus 34 times the speed of light, which is roughly 10 raised to 8, divided by lambda, which is 500 times 10 raised to minus 9. So if you just take the order of magnitude, what do you get? Anyone want to shout out at the answer?
Do you have an answer? Did you find out?
Yeah. Anyone want to guess an approximate answer for the first question?
Sorry. In electron volt, we can anything is on. Like electron volt is pretty nice number. 400.
Yeah, you can ignore these factors. Just give me an order of magnitude. We're all on the back of the envelope calculations here. So 10 raised to minus 34 multiplied by 10 raised to 8. So that's 10 raised to minus 26, right? Divided by 10 raised to minus 9, let's say. So minus 26 plus 9, 10 raised to minus, what's that? 17. Okay, Subhashish, did you have a number?
Yeah, close to 2.5 electron volt.
Okay, so is everyone okay with that?
It's in joule. So once you get it in joule, you divide it by 1.6. You can go minus 9.
Okay, if you're done with that, why don't you answer the next question? What is the energy of an infrared photon? The wavelength is about twice now, 1 micrometer. So 1 micrometer is, of course, 2 times 500 nanometers. So, and of course, you don't need to, yeah, I mean, anyway, I'll give you a few, 10, 15 seconds to think about this. Again, the goal here is just to get some order of magnitude. Yes, very good. So you don't, of course, have to redo all the calculation because you know there is this relationship, right? The energy is inversely proportional to the wavelength. If so, the wavelength is doubled, the energy has to be half. Okay? So I want everyone to get an insight into the relationship between color or wavelength and energy. Okay, so what have we learned from this? So first of all, let's summarize what we have learned. The first thing that we have learned is that the energy of a photon is very small, right? It's a couple of electron volts. Okay, and the second thing we have learned is that the energy of the photon is inversely proportional to the wavelength. So in other words, if you have infrared photon, it has half the energy of a green photon. Okay, these things are very, very important. We'll see as we go along. So just to reiterate, the energy of an infrared photon is less than that of a green photon. Okay. Okay, so moving on. Are there any questions? So it should be a pretty simple concept. So, okay. So the next concept we need to understand is photon flux. So of course, when we talk about actual systems, we're not talking about single photons. You have huge numbers of photons coming in, right, from the sun or whatever. So the photon flux is essentially is a metric which is defined as the number of photons per unit time per second per unit area. So it's the density of photons coming down to an absorber per unit time. Okay, so this is very important because, for instance, this determines the number of electrons generated in a solar cell. So in other words, if one photon gives rise to one electron hole pair in a solar cell, which we will talk about later on, then it's the number of photons that come in that determine the current generated in the solar cell, because the number of electron hole pairs give you the current in a solar cell. Okay, so let me reiterate. It is not the energy of the photon that determines the current generated in solar cell. It's the number of photons that came in, assuming the photon has sufficient energy. Okay, we'll see this again and again in the subsequent lectures, but it's a very important concept to keep in mind. So photon flux is, again, simple to define. It's just the number of photons divided by time times area. So it's in units of seconds per number per second per meter squared. Okay, written as phi. Okay, pretty simple so far. Now, but photon flux doesn't give any information on the photon energy. So you can say I have a million photons per second per meter squared coming into my solar cell, but if I don't know how much energy each of those photons have, I have no idea what the solar cell will do. Okay, so it's very important to understand how much energy there is in each photon as well. So then we can define power density. Power density is, as we saw before in the first week, it's watts per meter squared. It can be calculated by multiplying the photon flux by the energy of a single photon. So H, which is power density, is in watts per meter squared, is the photon flux, which is the number of photons per second per meter squared, multiplied by the energy of each of those photons. Okay, which is hc over lambda, which is now joules. Now, there's a very important caveat here, is that this, of course, is wavelength dependent. You can see it right there, right? So my power density depends on the color of the light, or it depends on the spectrum of the source. It's a very, very important concept here. Okay, and we'll try to do a few examples here. We're going to take a little bit of time because it's important to understand these concepts. And some of these concepts are simple, but they're a little bit subtle. So let's try to understand the implications of these concepts with some examples here. Okay, and I want you to discuss this with your neighbors because these are simple questions, but conceptual questions. And I can certainly ask you things like this in the exam. And it's important. I want you to gain insight into intuition from these concepts. So first question. Okay, if a red beam has the same power density as a blue beam, which beam has higher photon flux? Okay, I'll give you about 60 seconds. So discuss with your neighbor and or among your team members, whoever you want, and think about that question. And I'll shut up for a few seconds here. So let's think about this question in a very practical sense. So imagine I have a red laser pointer and I have a blue laser pointer, okay? And I know that with a power meter, I measured the same power density. In other words, I measured the power divided by the area of the beam. I know they're exactly the same. Now, which one is giving me more photons per unit area, per unit time? That's, of course, what I'm asking, right? Higher photon flux. So anyone wants to say what the answer is?
Blue.
Okay, and why? Any?
Frequency of blue light is higher, so the number of photons per unit area is higher.
Okay, so let's try to look in some detail. So first, you pointed out the frequency of the blue beam is higher. So that's good. That's correct than the red beam, right? Because we can go back to the spectrum. Now, how do you know? Of course, you need to know this. So you can go back and look at this and see, okay, my blue is on this side, my red is on this side. So the frequency is, of course, higher. Now, if frequency is higher, I know that the energy of my photon is higher, right? Energy is directly proportional to this, which is my frequency. Okay? That means my blue photon has higher energy than the red photon. Okay, so now let's come back to flux. Power density. So the power density is the same for both beams. Okay? This is the energy of the photon. It's different. So of course the flux has to be different because this product is the same. The blue photon, this number here is higher than the red photon. So what would you expect this to be for the blue photon? Has to be lower, right? So when the product has to be the constant. In other words, even if you ignore all the mathematics, just think from a common sense, each blue photon in my blue beam has a higher energy than each red photon in my red beam. Okay, think about these as blue marbles flowing, and this is the red marbles. My blue marbles have higher energy than the red marbles, but the total power density is the same, which means that I actually need to have fewer blue marbles to match the power density of the red marbles. So the answer is the opposite. Okay, I want you to think about this then before we move on. Okay, just to reiterate this, each of the blue photon has a higher energy than each of the red photon. So I actually need more red photons to match the total power of fewer blue photons. Okay, that's another way to think about it. Does that make sense? Okay, I mean, this is it's a little bit it's simple, but it's a little bit subtle. So you can go back and think about this at home a little bit more. Let's keep going, and then you will understand why this is important. So the next question, I want you to think about this next. Okay, let's take about 60 seconds also. If both beams are now incident on a solar cell, okay, the red beam and the blue beam on two different solar cells, let's say, which will produce a higher current? So in other words, I take one beam, put it on a solar cell. Take the other beam and put it on the solar cell. And I'm measuring the current from it. Which do you think will produce more current? And before you shout out the answer, just discuss, let's say for 30 seconds. We have to move a little faster. Okay, so any want to shout out an answer?
Red.
Yes, because the red now has more photons coming in per unit time per unit area, and as I said in the last slide, each photon is what gives you one electron hole pair in a solar cell, which is directly proportional to the current. Each electron hole pair gives you an extra current, right? Amperes is basically like number of electrons per second. Okay, so, and there is a very important assumption here, which I'll come back to, but assuming that both beams are exactly the same power density, so I take the same power density. So in other words, if I have the same laser beam width, I have the same power, and I shine it on a solar cell, just because the color is different, I will get different currents. Okay, that's a very, very important concept here. Okay. And there is a very important assumption here in that answer. And the assumption, we will come back to this several times during this class, is that I'm making the assumption that the red photon actually has sufficient energy to create an electron-hole pair in the solar cell. In other words, the red photon has energy higher than the band gap of the semiconductor used to make the solar cell. Okay, it's okay if you don't understand what that means. We'll come back to that later in the class. But that's the underlying assumption that those of you who have taken 3200, for instance, can appreciate. Okay, then let's go to the last question. Which will produce more electric power? And again, maybe discuss for 30 seconds or so. Okay, anyone? I didn't hear it, so you got to shout louder. Don't be shy. We are a small group here, and you can make mistakes. That's the only way to learn.
Red.
And why?
Higher current.
Yes. Okay. So okay, this may not be obvious to everyone, but the answer is wrong, first of all. And let's try to think, what is electric power? Those of you who are electrical engineers, what's power defined as? Current multiplied by what? Voltage, right? And voltage is determined actually by the energy of the photon. But let's not worry about the mathematics so much. Let's just step back a little bit and think about the common sense. I told you that both beams have the same power density, right? What's going into the system is the exact same power. Why would I expect the solar cell to produce different power, right? The answer is that I would actually get the same power for both situations. Okay, somewhat counterintuitive, but you will appreciate this later on, and I'll try to explain very briefly right now. So the answer to this question is they are the same. Okay, because the same power density going into the system, assuming that the efficiency is the same, which is of course an important assumption, but let's assume for the sake of the argument here, I would expect the same output from the solar cell. Now, why is this the case, even though that the red beam produced higher current? And the reason is because the red beam produces higher current at a lower voltage compared to the blue beam. Okay, and you will see this when we talk about solar cell basics. Okay, so I know I have confused you quite a bit, and that was the purpose. I want you to think about these simple concepts in a very intuitive fashion, not just mathematically. So you'll have to go back and think about these questions, at home or with your friends a little bit. But I want you to gain intuition from these ideas rather than just the mathematics. Okay, any questions? Okay, let's move on in the interest of time. So the next important property of light that we need to understand is referred to spectral irradiance. This is basically, I told you before that the dependence on wavelengths is very important, as you saw also in the previous example, in the previous slide. So spectral irradiance is essentially the power density as a function of wavelength, okay? And this is the most common way to characterize the light source. So this is an example of a spectral irradiance plot, of many plots here. So the horizontal axis is wavelength. The vertical axis is the spectral irradiance, which is in units of microwatts per meter squared per micrometer. So microwatts is, of course, power. Per meter squared gives me power density. Per micrometer means it's power density per unit of wavelength. Okay. And these are different sources. So solar irradiance is here, which is shown in log scale. This is log scale. That's by this pink plot. A xenon lamp is shown in the green. Okay, you can see that mercury lamp is here in red and the halogen lamp is in blue, and these are just showing how much energy is at each of the wavelengths. And as we saw in the last slide, this information is extremely important in order to figure out how much power you can actually get out of a solar cell, or what is the current being produced by a solar cell, and so on. Okay, again, we'll revisit this when we talk about solar cells, but I want you to understand the definition of what these things mean. The spectral radiance F is just H, which is the spectral power density from here, okay, watts per meter squared, divided by lambda, which is per unit wavelength. So you get phi, which is photon flux, times Hc over lambda squared. This is from the previous equation. Okay. Now, from here, we can also define what's called radiant power density, which is basically the total power density emitted from a light source can be calculated by integrating the spectral irradiance over all the wavelengths of interest. So if you want to see how much power density is coming out of a bulb or a flashlight or the sun, we simply take F, which is spectral irradiance, and integrate it over all the wavelengths of interest. Okay, you know F is a function of lambda, so F lambda d lambda. So let's very quickly try to understand. Units are very important here, so we need to think about this. What are the units of F? H. Now, F here is here, okay, which is H divided by lambda. And to go back here, H is watts per meter squared. Okay, power density. Watts F now is watts per meter squared divided by micrometers per wavelength. And then I'm going to multiply by wavelength again, my d lambda, so watts per meter squared per micrometer multiplied by micrometer again, so the micrometers cancel out. So I end up with H being the same as watts per meter squared, my power density. This is exactly what we're talking about, total power density, so it's watts per meter squared. Okay, you should, by the way, be able to very quickly understand what units are, and that's a very easy way to quickly check if your calculations are correct. If the units don't match up, then it's obvious something is wrong. So the way to compute the total power density is, of course, you have a plot like this for the sun. You essentially integrate the area under this curve. Okay, that gives you the total power. So for instance, if you want to see how much power density is coming from the sun, you integrate for over all these wavelengths, the area under this pink curve. Okay, and typically you use numerical techniques to integrate it, which I'm not going into, but you discretize this integral and you add these up. Not terribly important for us, but just keep in mind, because most of these things have to be done numerically, not analytically, because these curves are fairly complicated. Okay. Next concept that we need to understand is what's called blackbody radiation. This is very important because this allows us to simplify and these very complicated spectral irradiance plots and come up with some generalized principles that allow us to think about them. Now, blackbody, of course, is a approximation. An ideal blackbody, of course, does not exist. It's a physical approximation of reality. Okay. So light sources such as the sun, incandescent lamps, etc., can be modeled as blackbody emitters. An ideal blackbody absorbs all radiation incident on its surface and emits based upon its temperature. Okay, so, and you've seen this probably in your high school physics. You have blackbody radiation curves where you plot intensity as a function of wavelength, which is the same as what you saw before. You see curves which look like that. Okay, and each of these different curves represent different temperatures of the black body: 6,000 Kelvin, 4,000 Kelvin, 3,000 Kelvin, and so on. Okay. The spectral irradiance, we don't need, by the way, you don't need to know all the details here, but just for completeness, we should go through this. The spectral irradiance is governed by Planck's radiation law, which comes from some basic quantum mechanics. It's actually pretty simple. It actually comes from some statistical physics, so it's not that complicated. But anyway, you get some fairly involved equation which looks like this. This is, again, our very familiar now spectral irradiance, F, is a function of lambda for a black body, which has this formulation. Okay, where T is the temperature of the black body, H is the Planck's constant, C is the speed of light, lambda is the wavelength. So you can see it's a very strong dependent on wavelength, and because of this exponent, it has a very strong dependence on temperature as well. K is the Boltzmann constant. Okay, we'll come back to that later on. So the total power density of this black body here can be found by simply doing the integration that we talked about in the last slide. So this integration actually can be done analytically, doesn't need to be numerical. This can be done, okay? And you can actually do this. It's not that hard, but we won't do it now. You end up with a very simple expression. When you do this integral, you see that H is given by some constant sigma times temperature raised to 4. And this is referred to as the Stefan-Boltzmann law. So what this says conceptually, so sigma is simply a constant, which has units like this, 5.67 times 10 raised to minus 8 joules per second per meter squared per Kelvin raised to 4. This is called the Stefan-Boltzmann constant. What this law essentially means is that higher the temperature of a black body, I get more power density out of it. So the hotter my source, I get more power density out of it. So hotter my star, I get more power density out of it. Okay, so that's pretty intuitive, common sense, right? Okay. The next, and that's, you can see that in this curve here as the temperature increases. So this is 3000 Kelvin is this curve right there. 4000 Kelvin is right there. And you can see that the power density is, of course, the area under this curve. You can see the area is increasing, right? For 5000 Kelvins here, 6000 Kelvins here. So, okay. The next thing to think about is the wavelength where the spectral radiance is maximum. What I mean by that is this peak value here. Okay, so you see this radiance plot here. It has a peak value which refers to one color. This is wavelength. And that it changes with temperature. So this is 3000, the peak is around here. 4000, the peak is around here. 5000, peak is around here. 6000, peak is around here. Okay, it follows this curve right here. And it's a very important number. Let's think about this. Of course, to compute that is not that hard. You take the Planck's radiation law, the spectral radiance, and take the derivative of it and put it to 0. And you can do this. It's not that hard. And if you do it, you end up with a very, very simple expression which looks like this. Lambda of peak in micrometers is given by 2900 divided by T, temperature, in kelvins. And this is referred to as Wien's law. Okay? And this is obvious if you look at this curve. As the temperature increases, my wavelength decreases, right? It's a hyperbola as expected, like that. Okay? So just to summarize what we have learned in the last 2 slides, the temperature of the black body affects both the spectral distribution as well as the total power density emitted. So hotter the black body, I get more power density out, and I go shorter wavelengths in terms of its peak emission. Okay? So let's try to apply this law in a very, very simple case. Okay, this is a photograph, an actual color photograph of the Orion constellation. Okay, and let's compare between these 2 stars, Betelgeuse and Rigel. And I want you to think about which star is hotter by just looking at this picture and applying Wien's law. Just a few seconds. 10 seconds. You can discuss. Okay, anyone want to shout an answer?
Regal would be hotter?
Which one? Rigel?
Yeah.
And why?
Because it's more of a bluish spectrum, and red or whatever the Betelgeuse is.
Yes, very good. So if lambda is now blue, means of course it's smaller than for red. So T is inverse, so T is larger. So this is a hotter star than this. Okay, so you can see a very easy way, a very important way in which astronomers can use this information. Of course, we will also use this for other things later on. For instance, when we want to design lighting fixtures which have certain color responses, we need to be able to know, which source is hotter or which not. Okay, we'll come back to that. Okay, good. So now we have some understanding of the basic physics. Let's look at what's going on inside the sun. From a very, very simple point of view, the sun looks like this. It's a big ball of plasma, which means it's super hot gas. And what's going on is in the very, very center of this, nuclear reactions are happening, which essentially convert hydrogen to helium. So hydrogen atoms get fused to helium. Helium has 3 protons in its nuclei, and hydrogen has 2. So basically, fuse 2 hydrogen atoms together, you get helium. So the sun is a hot sphere whose internal temperature reaches over 20 million Kelvin due to nuclear reaction in its core. This reaction essentially produces the heat, which is about 20 million Kelvin. So that's the inner core. Then you have these gases which essentially circulate here, which take the temperature, this really, really hot inner core, and bring the temperature out. So there's a convection cycle that happens here. And it essentially takes the radiation from the inner core, absorbed by the hydrogen ions, closer to the surface. And the sun's surface, or the photosphere, which is about here, is about 6,000 Kelvin. So we can treat the sun essentially as a black body whose temperature is about 6,000 Kelvin. So what is the peak wavelength of radiation? We can simply apply Wien's law here. So 2,900 divided by 6,000. So it's about half, right? 2,900, let's say approximately 3,000 divided by 6,000 Kelvin. So 3,000 by 6,000 is half. So the peak wavelength is about half a micron. And that's approximately right. It's about there. Okay. And half a micron is roughly the green, which, by the way, is also the reason why human beings and most animals who are awake during the day have peak sensitivity in the green, because we have evolved to have peak sensitivity to the peak amount of energy coming from the sun. Okay. The solar spectral radiance resembles blackbody at about 6,000 Kelvin. Total power emitted by the sun is power density multiplied by the surface area of the sun, which we can compute from the Stefan-Boltzmann law to be about 9.5 × 10⁻25 watts. Just to review, the Stefan-Boltzmann law says H, which is the power density, is sigma, which is this number right here, multiplied by T⁴, T is 6,000. So if you work this out, you basically get this number, 9.5 × 10⁻25 watts, which is the power density multiplied by the area of the sun. So it's a huge number, obviously. Okay, very, very large number. Of course, sorry, just to clarify, the Stefan-Boltzmann law gives us the power density. It's this thing right here. You have to multiply it by the surface area of the sun, which is, of course, very large. And that's when you get this huge number. The spectrum itself looks like this, and we'll see this again and again, multiple times. This is a spectral radiance, again, in watts per meter squared per nanometer now. That's the unit of wavelength. And this is the wavelength in nanometers, going from UV, about 250 nanometers, to infrared, about 2,500 nanometers. So that's UV, visible, infrared. This gray plot here is the blackbody radiation at 5,250. So it's a little bit lower than 6,000. The yellow plot here is the sunlight at the top of the atmosphere, so in space. And this red plot here is the spectral radiance at sea level. And you can see there's a difference, and the difference has to do with the fact that there's some absorption in the atmosphere, which is determined by these gases that occur. So ozone absorbs here, oxygen absorbs here, water absorbs here, and so on and so forth. That's why you see these very sharp dips in the feature. So this obviously tells you something, that if you're trying to design a system to operate in space, for instance, for spacecrafts, that can have a very different incoming spectrum than if you're trying to design a system on Earth. Okay, this already tells you that, and it's very important to consider these things into account when you do these designs. Okay, so let's think about solar radiation in space. Solar irradiance on an object some distance d from the sun is found by dividing the total power emitted from the sun by the surface area over which the light falls. Okay, what does that mean? So that's our huge sun here, and these other planets. And each planet is, of course, at a different distance from the sun. So that means if you're at Earth, you're at some distance. The energy from the sun is essentially spread over a sphere which is equal to the distance, whose radius is equal to the distance between the Earth and the sun. Okay, and that's some big sphere here. Now, if you look at, say, a planet a little bit farther away, let's say Jupiter, it has a bigger sphere here, right? So the energy from the power density from the sun is the same. What's coming out is the same, whether it's Earth or in Jupiter. But if you're farther away, as you're in Jupiter, it's spread over a larger area. So per unit area, what Jupiter sees is much lower than what Earth sees. Okay, so it's very important to understand it's per unit area is very important, which is why we have life on Earth and not on Jupiter. So the way to think about this is relatively simple. You can look at the radiance, which is basically the sigma T raised to 4, just far familiar as Stefan Boltzmann law, multiplied by the surface area of the sun, 4 pi r squared, r being the radius of the sun, divided by 4 pi d squared, d is the distance between the sun and the planet in question, which is can be simplified as sigma T raised to 4 times r by d whole squared. Okay. And we can look at some of these numbers pretty quickly. So this is distance for Venus is about 108 billion meters, and the radiance on its surface is about 2,600 watts per meter squared. On Earth, we are about 150 billion meters. We are about, the radiance on the surface is about 1,366 watts per meter squared. This is actually in space, not on the surface of Earth. And if you're at Pluto, which is about 5,000 billion meters away, or 6,000 billion meters away, the power density is considerably smaller, right? 0.8, 0.9 watts per meter squared. So it's very, very cold. So if you want to really go into detail, which is not important for the class, but just so you know, the actual power density changes as the Earth moves because our orbit is elliptical and the sun's emitted power is not constant. Earth is closest to sun in January and farthest away in July. So if you want to consider that, you can have a more complicated expression here. Where n here represents the day of the year, and h constant here is the solar constant referred to as 1353 watts per meter squared. Okay, and you can look at that. For most purposes, we will ignore all the stuff, but just something you should be aware of. Now, of course, most variations are very small for most applications. So as in, since we are engineers, we always like to use standard spectra. So there are 3 kinds of standard spectra that are agreed to in the industry. AM 1.5, global, which is shown by this blue curve. Let's start with the red curve. It's easier to understand. This is called AM0. This is the STM standard number, so you can Google it, you can get it. National Renewable Energy Labs actually maintains these standards, so you can get this data. So if you ever want to characterize your solar cell, this is what everyone's supposed to use for proper certification. M0 refers to the spectrum in space, as we saw before. So that's this nice smooth spectrum. Okay. M1.5 direct, which is this green spectrum here, refers to the direct sunlight spectrum on Earth, on the surface of Earth. M1.5, we'll see what that means in a second, but just bear with me. So it's lower than the thing in space. The blue is the global spectrum. Now, the difference between global and direct, blue and red, is the fact that global actually includes scattered light as well. Direct refers to light that's directly coming from the sun. Scattered light refers to any light that is scattered in the atmosphere with the clouds and so on. So things are not coming straight from the sun. So that can be scattered from other things like clouds, water droplets, other molecules, dust particles, whatever, and scattered into your solar cell. So of course, the global spectrum includes both direct and diffuse, so it's a little bit higher. But as you will see later on, in concentrated solar photovoltaics, it's very hard to collect diffuse light. So most people think only in the direct spectrum. But if you're thinking about a standard solar panel, you usually think about it as a global spectrum. We'll come back to this later on as we talk about those specific subjects. So, as I said before, solar radiation on the Earth's surface is different than the solar radiation on the top of the in space. Okay, so the solar radiation incident on Earth's atmosphere is fairly constant. It's a very smooth curve, as we saw here. This red curve. There's some spikes here, but generally relatively smooth. The radiation of the Earth's surface varies widely due to atmospheric effects, including absorption and scattering in clouds, water vapor, dust, etc. Can also be due to local variations in atmosphere, such as pollution. So for instance, when we have inversion, we know it's very diffuse light that comes in. Of course, it can also depend on latitude, whether you're on the equator or whether you're in the tropics or you're far away from the equator or the polar regions. Of course, also season of year and time of the day. Parameters that change due to these effects are spectral irradiance, which is very important, as we saw before, power density, and angle of incidence. All of these are very important for the performance of any system. So we have to be aware of these and take these into account. The atmospheric effects can be also summarized by this nice little graph here, which shows how much energy is reduced due to scattering, absorption, and reflection. And we should also be aware that the spectral content itself, or the spectral distribution, also changes because absorption and scattering is wavelength specific. So in other words, the sky is blue because blue light scatters more than any other color. So that's why we see the sky as blue, right? Introduction of diffuser indirect component to solar radiation becomes important, particularly for concentrated solar photovoltaics. We'll come back to that. Local variations in atmosphere which affect overall power and spectral content. So again, you can read this curve, this figure like this. You have input of 100%. This is the absorbed part. So ozone absorbed a little bit, 2% in the very top of the atmosphere. You have upper dust layer which absorbs 1%, scatters a little bit. Some of it scattered into space, which is this arrow going up. Some of it scattered into the Earth, but at different directions, and so on and so forth. And at the end of the day, you end up with total absorbed of about 18%, scattered to space about 3%, and scattered to Earth about 7%. Okay, and if you subtract all that out, the direct to Earth is about 70%, as you see at the bottom. Okay. Now, of course, the atmospheric effects can also be characterized very carefully and depends on the molecules that are around. So it depends on ozone, carbon dioxide, water vapor. This causes all these very sharp absorption peaks, as we saw in the spectrum. Okay. Just to summarize this absorption, most of the far infrared, which is greater than 2 microns in wavelength, is absorbed by water and carbon dioxide. Most of the UV, which is less than 300 nanometers in wavelength, is absorbed by ozone, but clearly not enough to prevent sunburn. So, which is why people have to wear sunscreen. And we also know that in some places, when there's ozone depletion, like the ozone hole that occurred in Australia and so on, that can cause more UV to pass through because there's less ozone, and that can be very dangerous for sun damage. These cause deep troughs in the spectrum. Dust and air molecules absorb across the spectrum and reduce the overall power. So this is very, we've seen this, all of us have experienced this. When sun is overhead, all the wavelengths are uniformly absorbed and the sun looks white, right? But during the morning and evening, the optical paths are longer because the light has to travel through a lot of the atmosphere. And shorter wavelengths are more effectively absorbed and scattered, which means that the bluer part of the light is lost from the sun, which means the remaining part of the light is more enhanced, which looks reddish. So this gives it a reddish color and lower power density. So we can plot, for instance, the energy as a function of the time of the day. We know that sun rises because it's far, it goes through a lot of the atmosphere. The energy is lower. This is, let's say, energy produced by a solar cell or reaching the solar cell. And as you come towards noon, it goes up, and then it goes down again towards the end of the day. In equator, and these are different latitudes. As you know, as we go further and further away from the equator, you have to go through more of the atmosphere. So it goes down, as shown. And this is just to show shadows. Okay, so all of this is relatively common sense. Okay, now let's think a little bit more about direct versus diffuse sunlight. As I said before, direct sunlight is what comes straight from the sun with no scattering. Okay, diffuse sunlight is what happens to light that's scattered and reaches the absorber or your eye or whatever after multiple scattering events. Okay, And most scattering is referred to as Rayleigh scattering, which we might have seen in our undergraduate physics classes. Basically, it means there are tiny particles in the atmosphere that scatter light. And the Rayleigh scattering law essentially states that shorter wavelengths are scattered much more stronger than longer wavelengths. Okay, in fact, the dependence is in the order of power of 4 of the wavelength, so it's very, very strong. What this means is that blue photons will, which have shorter wavelengths, will scatter much more strongly than red photons, which is the reason why the sky looks blue. Okay, because that is the large fraction of the scattered light. As we saw before, about 7 to 10% of the light, even on a clear day, is diffuse. Okay, and the difference is not so obvious right now, but we will see it becomes very obvious when we talk about concentrating sunlight, because it's very, very difficult to concentrate diffuse sunlight. And most of the time, we'll only talk about concentrating direct sunlight. We won't actually be able to collect the diffuse light. So we need to be aware of what this is. So this is an interesting thing to think about. Is the fraction of high energy photons higher in diffuse or in direct sunlight? And this is a little bit poorly worded question. What I mean is that if you look at diffuse sunlight or if you look at direct sunlight, what color does it look like? And I've already answered it. Obviously, the diffuse light looks blue, whereas direct sunlight looks white. So, and the answer to that question is there, because blue has higher energy photons. It means that diffuse light has a higher fraction of high energy photons, right? Diffuse light looks blue, whereas direct sunlight looks white. So in other words, if you try to collect only direct light, you should be aware that you're throwing away quite a bit of the higher energy photons because of the scattering of those photons. And this will become more obvious as we talk about concentrating photovoltaics later on. This is just the curves again, just for reference. So we'll keep coming back to this many times. Now, this AM here, we saw this before, refers to air mass. Okay, and this is and we'll see what that means in a second. But just to define it more quantitatively, power density in AM 1.5 is about 28% less than in AM 0. Okay, as we can see, AM 0 is this red curve, AM 1.5 is this green curve, at least the direct. AM 0 is used to characterize solar cells in space. Okay. Effect of clouds is obvious. When you have a clear day, you had lots and lots of power, where on a cloudy day, you get that, which is mostly diffuse light, you get very low power. This is mostly direct light. This is direct and diffuse. Okay. Okay. A few other things to keep in mind is the human spectral response. So this is exactly the same curves as before. It's just plotted slightly differently. This is the direct sunlight. This is the diffuse sky. It's a little bit shifted. And this is the human spectral response. So just follow what these things are. So our eyes are sensitive here, which is roughly the peak of where our direct sunlight peak is. We'll come back to that, not so important right now. Okay, air mass. As I said before, I'll define what the AM in our plot in these plots are. So in this plot, for instance, what this AM refers to. It refers to air mass. Okay, air mass is the path length which light takes through the atmosphere, normalized to the shortest path possible. That's when the sun is overhead. It quantifies the reduction in power as light passes through air. So let's look at this slice of the atmosphere. This is the surface of the Earth. If the sun is right there, you pass through this much of air, x. If the sun is here, it passes through this much of air, which is y. And this is the angle theta. And AM is defined as 1 over cos theta, which essentially is a measure of how much longer has the sun passed through. So what is the air mass at sunrise? Anyone want to guess? But what's theta at sunrise? Anyone? Sunrise is way down here, right? Let's say down here. So what is theta? Anyone?
90.
Yes, theta is 90 degrees. So what is cosine of 90 degrees? 0. So 1 over 0 is infinite. So then talking about the air mass of infinity, right? But of course, that just means that the sun is just barely coming up. Anyway, I just wanted to make sure people are awake. If we take the curvature of the Earth into account, a more accurate formula can be derived, which is shown here, which of course we won't really worry too much about. Just keep that in mind. We could also have an expression for the direct component on a plane perpendicular to the sun's rays, which is given by this. Again, it's a power of air mass here. Intensity increases with height above sea level. So Utah and the desert Southwest is higher solar power because we are higher up, closer to the sun. Okay, so we get an expression here which includes the H, which is the height above the sea level. Again, for the purposes of our class, we will not go into this much detail. It's not that important. Just keep in mind again, just to reiterate, the diffuse component can be as high as 10% of the direct portion. Okay, so the last 10 minutes or so, I want to talk a little bit about the assignment and give you some examples of this of the project. So in this class, just to summarize what we have done so far, is just look at some basic understanding of light and basic understanding of sunlight in particular. We are going to use these concepts in the following lectures, okay? So the team projects are here, and we'll talk about that. Actually, let me just briefly mention the schedule here. Well, go back. So we are here. Okay, we are here. So we are going to use these basics in the subsequent lectures. On Thursday, we'll go through some basic thermodynamics. So these are the basic concepts we need to take, and we apply to some applications as we go along. Okay. So the first part of the semester is mostly understanding some of these fundamentals. That's the hope. Okay, so it's coming back to the project. So these are the teams. Hopefully everyone sees their name on there. So we have a team working on electrochromic windows. We'll see what those mean. The team will enlighten us. So another one, solar daylighting. Another one, solar water desalination. Solar refrigeration, concentrated solar, which can be photovoltaics or thermal or some hybrid. It's up to you. And we have a team working on solar water pasteurization. So what do we need for our first assignment? Again, just to reiterate, pick a team name, select a time to meet regularly as a team. Mode is okay. Use Canvas, chat, or forums for remote meetings. Submit a brief report via email as PDF on the following items. So this is the important thing which I didn't mention earlier. I want you to review current solutions in your project topic. So broadly in the topic assigned to you, look at what are the solutions available, what are the commercial solutions available, and if there are no commercial solutions, what are the research or academic solutions available. Discuss their pros and cons very briefly, and identify the main problems in your project topic. So what are the main issues with the current solutions? And the reason for this, by the way, is it's laying the foundation for your first presentation, which is, of course, very important. Okay, any questions about this before I move on?
Is this trained in individually or is this as a team?
Everything is as a team except for the midterm exam. So it's very, very important that you work together as a team. Any other questions? No? Okay, good. So I want to use the last few minutes to talk about some examples of some of the most common project topics here. So just to get your brain started thinking about ideas, okay? And I'll just, we have about 10 minutes left. So I'll just go through a few examples here just to get the ball rolling for you, okay? So first, the problem of water, which to me is one of the most important problems, as I said many times before. So, now we'll see a simple example here, but the question is, can you, or whoever the team is, make a simple, cheap, portable, system for desalination, pressurization, whatnot. So let's take a quick look at this example. First of all, can you hear this, the video?
Oh.
Can you not hear the video, the sound?
The sound is not there.
Okay. So maybe I'll just let me see if I can. I'll narrate it, I guess. Not quite sure why the sound is not there. Actually, you know what? Maybe I know why. Hold on. Can you hear it now?
Yeah. No. Your computer sound doesn't play through your video service.
Illumination facility. So once again, we're
Can you hear
continuing
Yeah.
Solar Village, and here's an example of a very simple, very primitive desalination facility that can be used to remove salt from like ocean water or seawater, and also to clean the dirty water. And this is completely free except for, you know, the cost of the actual equipment. So basically what you have inside is black surface. You pour salt water inside and you have this glass dome, this glass pyramid. So what happens? The solar heat evaporates the water goes up and it ends up on this glass, and then it drips down, comes here, and is collected here. So now you can drink that water, it's pure. And basically this, it's a little bit more than a square meter, but you can get about 10 liters of pure water from this thing per day, 10 liters from this here. So 10 liters is basically enough for one person for one day. So this is a very clean and efficient way, but the problem with it, it uses a lot of space to create a lot of water, which can affect the environment. So that's always the, you know, the argument for building these massive facilities of evaporating and cleaning the water this way. Now, a lot of water desalination actually uses energy, fossil fuels, and it can produce a lot more water in a much smaller space. So that's what's being done in Israel. Actually, now Israel produces 60% of its fresh water from seawater, but it uses a lot of energy. And this is completely energy free because it uses solar heat to produce water. And on small scale, I think this is the best from the environmental perspective. But once again, if you need a lot of fresh water, you would use a lot of space. And actually, this is very cheap to build. But once again, if you use a lot of space, it can affect the environment. So, all right, this was Leo.
Okay, perfect. So that's an example. Let's move on to another one. So this is essentially a hybrid system which talks about photovoltaics and heating. Okay, and this is again related to the second lecture that we went to. And the question is, you know, can you design a system that's inexpensive, portable, has high efficiency? So let's take a quick look at what this is all about. Oops. Let's see. This is a solar concentrator system, really. And it's pretty self-explanatory, actually. I don't think there's any text, but it uses a parabolic trough system, which tracks the sun, and there is a liquid that goes through the focal plane, the focal line of this parabola. And you can clearly see the tracking of the sun there. Okay, so you can see it has a 10x concentration, which means it's collecting light over an area of 10 times as big as the area of the absorber. And we'll see that later on, that tracks the sun. And you pass liquid, as shown there, which heats up, blue to hot. And you can use the hot liquid to either run a heat engine to generate electricity, as we saw in this first week, or you can use it directly for heating purposes directly. And it's a hybrid system in the sense that it's taking the heat directly and you can apply it for either electricity generation or heating purposes. And you can array them, which is the example that we're talking about, is a modular system. Okay. So the next example is relevant to one of the themes, which is solar refrigeration and cooling. Again, the question we're trying to answer is, can you design a simple, portable, cheap refrigeration cooling system? So let's take a quick look at this solution here. Oops.
specialist here at Sopogy, where we're creating simple solar technology solutions for commercial, industrial, and utility clients. In this episode of Sopo How, I'll explain how our micro CSP parabolic trough technology is used to create solar air conditioning. In solar air conditioning, a set of Sopogy micro CSP Soponova troughs are connected to a thermally activated chiller running on heat. Different types of thermally activated chillers are absorption, or desiccant systems. Adsorption and desiccant chillers are less common, so we'll focus on the absorption chiller principle. In these systems, water, the refrigerant, absorbs heat at a low temperature and low pressure during evaporation and releases heat at a high temperature and high pressure during condensation. Lithium bromide solution, which acts as the absorbent, is used to absorb the vaporized refrigerant. The evaporation of the refrigerant takes place at a low pressure. The diluted solution, which contains the absorbed refrigerant vapor, is heated at a higher pressure. As lithium bromide becomes dilute, it loses its capacity to absorb water vapor. It therefore needs to be reconcentrated using a heat source. This leads to the vaporization of the refrigerant, and thus the solution is restored to its original concentration. The cycle keeps repeating itself to give the desired chilling effect. Absorption chiller system efficiencies are often around 0.7 COP, or coefficient of performance, for a single effect, or 1.2 for a double effect absorption chiller, making for a good complement to the efficient Sopogy micro CSP solar collector. Soponova is the ideal technology for solar air conditioning.
Okay, so we'll move on, but that's an idea. And then there's one for solar daylighting. So I'm going to post all these links on the website, but that's basically the last slide. So let me stop here.